Fighter jet engines burn at 2000 degrees Celsius, hot enough to turn steel into liquid. The turbine blades spinning inside experience temperatures 400 degrees above their melting point. Yet right now, 10,000 aircraft are flying with engines running hotter than the materials they're made from should physically survive. The GE-90, powering a Boeing 777, operates at temperatures that would instantly vaporize aluminum. The F119 engine in an F-22 Raptor generates heat that liquefies titanium. These machines violate everything your engineering textbook told you about material science. The metal components should be puddles of molten slag within seconds of ignition. Instead, they operate for 20,000 hours between overhauls, spinning at 15,000 RPM while glowing white-hot. You're looking at one of humanity's greatest victories over the laws of physics, an engineering solution so counterintuitive that when jet engine pioneers first proposed it in the 1940s, metallurgists said it was impossible. They were wrong. Inside a modern turbofan engine, compressed air reaches 700 degrees Celsius before fuel even ignites. When jet fuel combusts in the chamber, temperatures spike to 2000 degrees, hotter than lava erupting from a volcano. This superheated gas blasts through turbine stages at supersonic speeds, transferring energy to blades that must withstand forces equal to hanging a fully loaded semi-truck from each blade tip. The nickel superalloys used in these turbines have a melting point of 1,350 degrees Celsius. Basic physics says they should liquefy instantly. They don't. Understanding why requires examining 4 revolutionary engineering breakthroughs that transformed impossibility into routine operation. The first breakthrough came from rethinking metal itself. Traditional turbine blades were forged from polycrystalline metals. Billions of tiny crystal grains joined at boundaries. Under extreme heat, these grain boundaries become weak points where cracks initiate and propagate. Engine designers realized they needed to eliminate grain boundaries entirely. Enter directional solidification. Engineers at Pratt & Whitney developed a casting process that creates turbine blades from a single crystal of metal. Not thousands of crystals, not hundreds, one crystal. The entire blade, from root to tip, consists of atoms arranged in perfect crystalline alignment. No grain boundaries means no weak points for high-temperature failure. Creating these single crystal blades requires precision that borders on absurd. The molten superalloy gets poured into ceramic molds containing spiral channels called pigtails. As the metal cools at precisely controlled rates, sometimes just 2 degrees per hour, crystal growth follows a specific direction. Only one crystal survives the journey through the spiral. That survivor becomes the entire blade. Manufacturing defects that would be acceptable in any other component become catastrophic here. A single misaligned atom cluster can create a stress concentration point that fails after a few hundred hours instead of 20,000. Quality control uses electron microscopes to inspect crystal structure at magnifications where individual atomic planes become visible. The second breakthrough revolutionized cooling without using cold air. Engineers realized they could protect blades using air from the compressor section at 650 degrees Celsius. Still scorching hot, but 1,350 degrees cooler than combustion gases. This cool air flows through intricate passages inside each blade, removing heat from within. These cooling channels aren't simple tubes, they're serpentine passages with turbulators. Tiny ridges that create vortices disrupting boundary layers and tripling heat transfer rates. The channels branch and merge following paths calculated by supercomputers modeling thermodynamic flow at molecular levels. Some passages measure less than a millimeter wide, maintaining dimensional tolerance of plus or minus 0.005 of an inch. Manufacturing these internal passages pushes casting technology beyond conventional limits. Engineers inject ceramic cores into blade molds before pouring metal. After solidification, they dissolve the ceramic using caustic baths, leaving behind hollow channels following paths impossible to machine conventionally. Advanced blades contain over 300 individual cooling holes, each angled precisely to maximize heat extraction while minimizing aerodynamic losses. The cooling air doesn't just flow through blades. It creates an invisible shield around them. Film cooling represents the third breakthrough. Hundreds of laser-drilled holes, each smaller than a human hair, allow cooling air to bleed through the blade surface. This air forms a protective boundary layer, insulating metal from direct contact with combustion gases. The physics behind film cooling defies intuition. You're using 650-degree air to protect against 2,000-degree gases. Success depends on maintaining laminar flow characteristics that keep the cooling film attached to blade surfaces. Too much cooling air wastes energy. Too little allows hot gas entrainment that burns through blades in minutes. Computer simulations run for weeks, calculating optimal hole patterns. Each hole gets positioned at angles between 20 and 35 degrees to the surface, with compound angles accounting for rotational forces and pressure gradients. Manufacturing tolerances measure in microns. A hole drilled 5 degrees off angle reduces cooling effectiveness by 40%. Modern laser drilling systems fire 20,000 pulses per second, each pulse removing a few molecules of metal. Drilling a single cooling hole takes hours. A complete turbine blade requires 6 weeks of continuous laser drilling to create all cooling passages. The laser must account for thermal expansion during drilling. The hole location shifts as surrounding metal heats and cools. The fourth breakthrough came from ceramic technology borrowed from spacecraft heat shields. Thermal barrier coatings protect blade surfaces using materials that withstand temperatures no metal can survive. These aren't paint or simple oxidation barriers. They're engineered ceramic systems with properties precisely tailored for jet engine environments. The coating system uses multiple layers with different functions. First, a metallic bond coat containing aluminum and chromium provides oxidation resistance and thermal expansion matching. Above that, a ceramic layer of yttria-stabilized zirconia creates the thermal barrier. This ceramic has thermal conductivity 10 times lower than steel, maintaining a 200-degree temperature drop across a coating just 300 microns thick. Applying these coatings requires either electron beam physical vapor deposition or plasma spray techniques. In EBPVD, electron beams vaporize ceramic ingots in vacuum chambers. The vapor condenses on rotating blades, growing columnar structures that accommodate thermal expansion without cracking. The columns measure 5 microns wide, 1/20th the width of human hair, and must maintain uniformity across complex blade geometries. These 4 technologies working together enable modern engines to operate in conditions that destroy lesser materials in seconds. But success requires perfection. A blocked cooling hole, a degraded coating section, or a microscopic crack in the single crystal structure triggers cascade failures. Engineers combat this using real-time monitoring systems tracking blade health through vibration signatures. Accelerometers detect frequency shifts indicating crystal structure changes. Pyrometers measure blade surface temperatures accurate to 2 degrees. Borescope inspections between flights identify coating degradation before it becomes critical. Maintenance protocols reflect the extreme demands on these components. Every 3,000 flight hours, engines undergo hot section inspections. Technicians use fluorescent penetrant testing to reveal surface cracks invisible to naked eyes. Eddy current testing identifies subsurface defects. X-ray diffraction analysis confirms crystal structure integrity. The economic implications stagger comprehension. A single high-pressure turbine blade costs $25,000. A complete engine contains 60 to 80 blades depending on design. That's $2 million in turbine blades alone. The investment pays off through fuel efficiency gains that save airlines millions annually. Modern engines achieve thermal efficiency approaching 55%, double what was possible in early jets. Every degree increase in turbine inlet temperature improves fuel efficiency by 0.5%. Across a fleet of 100 aircraft, that translates to $50 million in annual fuel savings. Military applications push even further. The F135 engine powering F-35 fighters operates at temperatures classified by the Pentagon. Unofficial estimates suggest turbine inlet temperatures exceeding 2,100 degrees Celsius. These engines must survive not just cruise conditions but combat maneuvering, generating G-forces that multiply blade stresses tenfold. Research continues pushing boundaries. General Electric tests ceramic matrix composites that maintain strength at 1,650 degrees Celsius, 300 degrees higher than current superalloys. These materials could eliminate cooling air requirements, improving efficiency another 15%. Additive manufacturing opens design possibilities impossible with casting. 3D printed blades incorporate cooling channels following mathematical curves that optimize heat transfer while minimizing pressure losses. Internal lattice structures reduce weight while maintaining strength. Powder metallurgy creates alloy compositions impossible through conventional melting. Universities research shape memory alloys that change cooling hole geometry based on temperature. At cruise conditions, holes partially close to minimize efficiency losses. During high-power operations, they open fully for maximum cooling. Smart materials could extend blade life 50% while improving fuel efficiency. The next time you board an aircraft, remember you're trusting physics-defying engineering. Those engines hanging from the wings operate in conditions that shouldn't be survivable. They work because engineers refuse to accept material limitations as permanent barriers. Every commercial flight represents thousands of turbine blades spinning at speeds where centrifugal forces try to tear them apart, in temperatures that exceed their melting points for hours without rest. They survive through engineering precision where success is measured in atoms and failure means catastrophe. This is why jet engines don't melt. Not through one breakthrough, but through 4 integrated technologies working in perfect synchronization. Single crystal metallurgy eliminates structural weaknesses. Internal cooling channels remove heat from within. Film cooling creates protective barriers. Ceramic coatings insulate surfaces from extreme temperatures. Together, these innovations transform 2,000-degree hellscapes into manageable working environments. They represent humanity's refusal to accept impossible as an answer. The engines powering modern aviation exist because engineers looked at melting points and said, "We'll find another way."